Well, hello there and welcome from Sacramento, California to today's Inside GNSS Inertial Integration Applying the Technologies webinar, sponsored by KVH and Inside GNSS and hosted by WebAttract, your end-to-end solution provider for informational webinars. Hi, I'm Mike Agron, Executive Webinar Producer with WebAttract, and I'm going to be one of your moderators and hosts for today's session. In just a moment, we're going to be introducing our panel of thought leaders, because what today is about is hearing from these experts as they discussed, amongst other topics, trends in GNSS inertial integration, especially dealing with GNSS challenge environments through finding a path from specific integrated inertial implementations to generic all-source integrated solutions. Now, you're also going to have an opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Experts panel session with the panelists. But first, let's talk a little bit about who's in the audience, because we got quite an audience. Over 700 of you have registered from 59 countries, 31 states and provinces, representing the following roles. You can see the percentage of where you fall into. We're absolutely delighted to have you here. And I should also mention that our panel is also global, from Sydney to Calgary and Florida. It is my pleasure to bring on and introduce from Inside GNSS, Richard Fisher, the Director of Business Development, who's going to give you an official welcome. And let's get started. Hi, Richard. How you doing?
Thank you, Mike. Welcome to the latest installment in the Inside GNSS web seminar series. We're delighted you're all here. Today's presentation is sponsored by KVH Industries and addresses a subject of rapidly growing concern for GNSS product designers, service providers, and users. That is, practical applications of integrated GNSS and inertial navigation systems, especially in signal-challenged environments. Inside GNSS reaches more than 35,000 readers around the world with our print edition and tens of thousands more with our digital magazine and newsletter. And based on the over 700 registration for today's webinar, it's clear that GNSS and inertial navigation integration are matters of considerable interest to many of you. Inside GNSS webinars follow the same approach as we take to our engineering-oriented articles in the magazine, to take up issues of current importance to the GNSS community and bring subject experts to help us explore those topics in depth. I encourage those of you viewing our presentation today to contribute to the webinar as well by responding to the questions in our online webinar polls and sending in your questions for the live question and answer periods that will take place during the event. And now I would like to invite Jay Napoli, Vice President of Fiber Optic Gyro and OEM Sales at KVH Industries, to say a few words about today's event. Jay?
Thank you very much. Hello, everyone. Thanks for joining us today. We're pleased to sponsor today's webinar in conjunction with Inside GNSS. Many of you know KVH works extensively in the fiber optic gyro or FOG field to include FOG-based IMUs and inertial navigation systems. We fielded well over 50,000 fiber optic gyros globally. The integration of inertial navigation technology with GNSS is a topic that's been heating up for quite some time, and KVH works extensively in that arena. In fact, we're probably most likely working with many of you who are listening to today's webinar. So we've got a large range of small and large customers. They include things like defense contractors, systems integrators, commercial customers with industrial/commercial systems, and a number of technology innovators. So today I'd like to thank Mark Petavello. Mark's a geomatics engineering professor at the University of Calgary. He's acting as our moderator. And I'd also like to especially thank our panelist, and Andrei Solovyev. He's the president of QNAV, which is a Florida-based R&D business enterprise, and Xavier Orr, an R&D engineer of 3D navigation. Xavier is actually joining us from Sydney today, so he's in very early. He's also the co-owner of Advanced Navigation Pty Limited, again in Sydney, Australia. So they've put this all together, and the information that we presented today hopefully will be of value to everyone. So in the interest of getting right to the topic at hand, I'd like to turn this back over to Richard Fisher at this point. Richard?
Thank you, Jay, and greetings to our worldwide audience from all of us at Inside GNSS. Mark Petavello will be our moderator. Dr. Mark Petavello has been actively involved in the navigation community for more than 15 years and has received numerous awards for his work. Dr. Petavello is also a contributing editor for GNSS Solutions column of Inside GNSS magazine. Mark, it's great to have you here with us again today. Welcome. Mark?
All right, thanks a lot, Richard. To extend the welcome on behalf of the magazine, I'd like to welcome everyone from far and wide to the webinar today. We have two excellent panelists here who are going to share their knowledge on GNSS INS integration, and hopefully you guys will all learn a lot that you can take back to your respective applications. Before we get to the panelists, I want to spend actually just a couple minutes talking about how this webinar fits in with the other ones that have been offered by Inside GNSS over the last few years. So back in late 2009, we had what I am calling the nuts and bolts presentation. This was really kind of fundamental equations, equations of motion, mechanization equations, the basic building blocks that you would need to build any type of GNSS INS system, along with some demonstration of some possible results. Following that, just over 2 years later, we had what I'm calling the filling in the gaps presentation, and this was focusing a little bit more on how do you select an integration strategy when you're integrating these two types of systems. What are the practical considerations, time tagging issues, how do you read a spec sheet, how do you fill in the blanks that aren't on the spec sheet, and ultimately how do you start designing a system that you can ultimately use. And that leads very nicely into today's presentation, which is really about applying the technologies. And without giving away all the details, we're going to be looking at some of the trends and the key challenges associated with inertial navigation, especially in degraded type environments, some of the solutions to that, and the resulting applications that KVH and advanced navigation have ultimately been able to produce as a result of that. So having said that, before we get going, I'd like to turn it back to Mike to pose our first poll question.
Thank you, Mark. Thanks. So, folks, I'm going to launch a poll, and if you'll take a look at it, it should be up in your screen right now. I'd like you to select one. And what would you say is the greatest challenge with integrating GNSS INS? Is it modeling the inertial errors? Is it 2, identifying good or bad GNSS data? Or is it how to integrate other sensor data? Or 4, selecting architectures for GNSS INS integration? And now I'm going to go ahead and share the results. And Mark, I'll turn it back to you to give any commentary that you'd like.
All right, well, thanks a lot, Mike. So relatively even distribution of feedback there, and I think fortunately for everyone in the audience, you'll definitely see all of these topics touched on today during our presentation. So without further ado, I will take the opportunity to introduce our first presenter, who's Dr. Andrei Solovyev. Andrei is a part-time researcher faculty at the University of Florida, and as was previously mentioned, the president of QNAV, based out of Florida. He has previously served as a senior research engineer at the Ohio University Avionics Engineering Center. He has authored many papers on navigation-related publications, at last count, over 80. And his research interests are in the area of sensor fusion and signal processing for navigation. And Andrei is going to kick us off today, giving us a bit of an overview of GNSS INS integration and some of the basic tools that we're going to need to get there. Andrei, the floor is yours.
Right. Thank you, Mark. So I'm going to set up the stage for today's technical discussion and overview main principles of GNSS and inertial integration. So as we all pretty much know, the main reason for combining the GNSS and inertial navigation technologies is because we want to combine complementary features of these two navigation sensors. Inertial is a completely self-contained system that works at any environment at any time. However, inertial navigation solution experiences drift over time. And as a result, for most of the applications, it's only usable for a fairly limited period of time. So on the other hand, GNSS is a driftless navigation solution, but it's susceptible to interference, both intentional and unintentional. So the idea is obviously to combine these two navigation systems to provide something which is I would call semi-self-contained without drift. So the way to combine inertial and GNSS navigation solutions is to have INS as a core sensor because it works at any environment at any time, and use GNSS to provide reference data in order to reduce drift in inertial navigation outputs. And on the other hand, inertial data can be also used to improve the GNSS robustness, specifically robustness of the GNSS signal processing part in the environments like weak signal environments or under interference. The current status of the technology, there's obviously a fairly wide range of GNSS inertial products. And examples are embedded GPS, INS, IGI for military applications. The limitations, they're using relatively high-grade, expensive inertial units. And also, there's a bunch of OEM GNSS inertial products for ground and aerial applications. Again, for most of them, the limitation is that they use a fairly sophisticated inertial units, fairly expensive inertial units, and they still rely quite a bit on GNSS capabilities. So they're not designed to operate in limited GPS or GNSS environments or GPS-denied environments. The development trends in the GNSS inertial integration area, definitely we're trying to go from high-grade inertial products to low-cost consumer-grade sensors. And this is obviously especially driven by smartphone applications and personal navigation devices for location-based services. We're trying to get from open sky environments to urban canyons, indoors, and even underwater applications where GNSS navigation capabilities can be quite limited or completely denied. And we extend in the system architecture from a classical GNSS inertial integration approach to include other sensors, what I would call INS integrated with GNSS Plus, where we're not only using satellite measurements, but we include measurements from other sensors such as video camera, LiDARs, maps, motion constraints, etc. So in a sense, we're trying to use any type of navigation-related information that is available to us in order to reduce drift in inertial navigation outputs. So what's the right integration approach? There are three integration modes. A loose integration, which is the fusion at the level of navigation solutions, tight integration, where we fuse in navigation measurements, and deep integration, which integrates sensor data at the signal processing level. So loose integration obviously has fairly limited capabilities in GNSS challenged environments. I put the example here. If you have, in urban environments, you can have a fairly sparse GNSS position fixes, and you won't be able, for those cases, you won't be able to use, you don't have any reference data to help your inertial if you're using the loose integration approach. However, even in very dense urban canyons, sometimes or most of the time, I should say, you generally have 1, 2, or 3 satellites, and those satellites are not available. It's not sufficient to compute GNSS position and time and fix, but if you're using a tight or deep integration approach, then some data is generally still available for integrating with the inertial and reducing drift in inertial navigation outputs, at least to some extent. So to me, when we're talking about the integration of the GNSS and inertial, and specifically extending the integration techniques to include other sensors, then tight and deep integration are much more efficient, much more suitable for GNSS challenged and GNSS denied environments. A data fusion tool for GNSS inertial, we all know it's a complementary Kalman filter. So the complementary Kalman filter, we not estimate the motion states themselves, we estimate errors in inertial navigation outputs. That simplifies the dynamic modeling quite a bit and allows for the linearization of most of the system relations. So the way it works, essentially, we have a prediction of the measurement based on the inertial. Then we have the actual measurement. We take the difference, linearize it using the first order Taylor series expansion, and then use the results to update inertial error states. And sometimes the error states of the reference sensor, that is GNSS receiver in this case, are also included into the Kalman filter state vector. In the receiver case, we obviously include the receiver clock bias and the receiver clock drift as an additional states. The two major assumptions of the extended common filter, first of all, you got to be able to linearize your system fairly efficiently. In other words, non-linear terms have to be fairly small. And also the common filter assumes Gaussian error distribution. And for the GNSS inertial case, it works pretty nicely for most of the cases, unless you're dealing with a really low-grade inertial and your attitude errors drift fairly significantly. Then you extended common filter may have a problem. But for most of the cases, the apparatus of the extended common filter is suitable for the GNSS inertial integration. However, when we extend the technology to include other sensors, then the common filter is not necessarily the best option, and you may want to use nonlinear filtering techniques. For example, if you want to restrict your solution to the hallway layout, in other words, you want to somehow incorporate the information that your trajectory cannot cross over the walls or cannot cross through the walls, then the extended common filter, it's not really the right approach to put that constraint in. In this case, a particle filters may be a much more suitable mechanism for correcting inertial drift. And I'll talk about the particle filter application and particle filter concept towards the end of this webinar. So the bottom line is that the extended common filter works for GNSS inertial, but for INS GNSS Plus, we may want to involve some nonlinear filtering techniques. And at this point, I'll give it back to you, Mark.
Great, thanks a lot, Andre. And before we continue on, I'd like to introduce our second panelist today, Mr. Xavier Orr, who, as was stated earlier, is a lead software engineer at Advanced Navigation, based in Sydney, Australia. He leads the company's software team in R&D of inertial navigation, data fusion and estimation algorithms, RF positioning, and sensor technology, so certainly very well suited to be here today. He sits on the company's product planning team. He specializes in artificial intelligence algorithms, control algorithms, sensors, and robotics. And finally, he holds a bachelor's degree in mechatronic engineering and computer science from the University of Western Australia. So welcome, Xavier. And Xavier is going to talk to us about some of the biggest challenges facing the integration of GNSS and inertial navigation. Xavier, it's all yours.
Yep. Hi, everybody. So in this section, I'm going to go through an introduction to the motivations for development and the challenges faced in the inertial navigation system that we developed in collaboration with KVH. We determined that there is a market hole for a system with very good long-term dead reckoning. We also found that there's a demand for the ability to initialize and maintain heading long-term without GNSS and insusceptible to magnetic interference. We went about designing a system that extends our current artificial intelligence filters with some additional algorithms for north-seeking and making use of KVH's FOG technology. We decided to use as many sensor sources as possible to really squeeze out all possible information and get the best dead reckoning possible. In addition, we had a price target of $30,000 US. We started nailing down the requirements, and one of the main requirements for long-term dead reckoning is highly accurate orientation. Although we actually use quaternions in practice, orientation is best thought of as the three Euler angles roll, pitch, and heading, shown there in the picture. These are tracked by the gyroscopes and corrected for errors from the gravity vector and other sources. To determine accurate roll and pitch, accelerometers with high bias stability are essential to provide a reference gravity vector. It is also desirable to have a low starting bias, as the system must take time to track any bias on startup, and a lower initial bias means faster startup time. Once you have accurate orientation, you need high accuracy gyroscopes to maintain that orientation accuracy. It is essential to have very high bias stability gyroscopes, as any change in bias must be tracked and will increase reliance on correction sources, which will reduce overall accuracy. So the gravity vector can be used for a reference for roll and pitch, as shown in those two images there. So the possible sources of heading are the traditional magnetic heading. There's GNSS velocity heading, north-seeking gyro compass heading, and external references such as ground markers and radio systems. For a system focused on dead reckoning, we must consider the only usable, always available sources of heading are magnetic and north-seeking gyrocompass heading. Magnetic heading has been used for navigation since the Middle Ages. However, it does have some downsides. When determining magnetic heading, you are trying to measure the Earth's magnetic field. However, interference sources can make this difficult. Ferrite metals and current-carrying wire cause significant disturbances. In today's high-tech environment, these interference sources are prominent. So we come to the conclusion that magnetic heading is not reliable for a high-accuracy absolute reference, but it is good for a relative reference to determine when your heading is stationary. Now we come to north-seeking gyrocompass heading. And north-seeking gyrocompass heading is based upon the principle of measuring the Earth's rotation. To do this, you have to separate the Earth rotation from the gyroscope bias, gyroscope noise, and other error sources, which includes movement of the whole system. This is a delicate balancing act, and to do it well, it requires high bias stability gyroscopes. So after researching a lot of manufacturers, we found the KVH Industries 1750 IMU to be the best commercial gyroscopes available. They provide excellent gyroscope bias stability of 0.05 degrees an hour, which allows for both north-seeking and maintaining high accuracy orientation. Additionally, the accelerometers used in the 1750 IMU combine both a low initial bias and excellent bias stability in operation, which allows for fast initialization and minimal bias-induced errors. And back to you, Mark.
Great, thanks a lot, Xavier. I will turn it over to Andre to give us an overview of the initial alignment and motion constraints. Andre.
Thanks, Mark. So I'm going to dive into a little bit more technical details, some theoretical background. How do you do initial alignment and how you apply motion constraints? And these two topics are of particular interest when you integrate in a GNSS with a little bit lower cost inertial sensors. So we'll start with the initial alignment or attitude initialization. How do you estimate, how you determine initial attitude? And the motivation is obviously inertial is a dead reckoning solution that needs to be initialized before we can actually use it. So position and velocity initialization steps are fairly straightforward when GNSS is available. So you just use GNSS position and velocity as your initial position and velocity for the inertial. The attitude gets a little bit trickier. So how to initialize the attitude? So I'm going to talk a little bit about that. So we need, in general, we need to know at least two vectors. We need to have projections of two non-collinear vectors, A and B, in navigation frame where we want to resolve our position and velocity solution, and inertial body frame, which is defined by the orientation of sensitive axis of accelerometers and gyros. So we know these two vectors in navigation frame and body frame. So the initial attitude alignment procedure needs to find the rotation of the body frame such that after that rotation, the components of these two vectors in the navigation frame and the body frame are completely aligned. And I'll explain in just a few minutes why do we need two vectors, why just not one, to complete the initial attitude alignment. Generally, when I'm talking about the rotation of the body frame to align vector components, I mean the computational rotation. Most of the time we're doing this with the strap-down inertial, it's not a gimbal system, so we're not mechanically rotating the system, it's a computational rotation here. And also, for the sake of this presentation, I'm using direction cosine matrix, this one over here, to denote the attitude, but other forms of the attitude representation are also can be used, obviously. Xavier mentioned quaternions. Quaternions can be used as well. So the first step, we need to align vector A in the navigation and the body frame. So we need to find the rotation, C1 here. After this rotation, the components of the vector A in the body frame are exactly the same as these vector components in the navigation frame. So it can be actually shown that we have this vector A before and A after, defined by the body frame components, and the navigation frame components. So the rotation axis is perpendicular to the planar surface that is defined by these two vectors, A before and A after. And the rotation angle is the angle between these two vectors. So there's a standard expression how you define the rotation matrix or quaternions given the rotation axis and the rotation angle. And we'll put some list of technical references at the end of this webinar so you can find more details how it's actually done. But conceptually, this is how it works. And after the first step, the first vector, the vector A, is aligned in the navigation and body frame. The caveat is that it's not necessarily sufficient to align one vector and align two coordinate frames as a result. Because when you rotate the coordinate frame around a certain vector, the components of that vector do not change during that rotation. So as a result, there's an additional degree of freedom, in this case, the rotational freedom around vector A, that needs to be compensated before we can claim that the two coordinate frames are completely aligned with each other. And that's why we need the second rotation and the second vector B, which has to be non-collinear to the vector A, because otherwise, if we have two parallel vectors, obviously we don't have any additional information in terms of the rotation. So the second rotation step, obviously we don't want to change components of the vector A. It's been already aligned, so we're rotating the system around the vector A and making sure that components of the vector B are aligned at the end of this second rotation, C2. And initial orientation is estimated as just as a product in case of the direction cosine matrices, just as a product of C2 by C1. This is your initial orientation. So the question is which two vectors we want to use for the initial alignment. The classical approach, vector 1 is the acceleration due to gravity, and the earth rate is the second vector. The problem is the gravitational acceleration can be measured by any type of accelerometers. Obviously, if you can't measure the acceleration due to gravity with your accelerometers, you have a serious problem with your system design. The earth rate requires a fairly sensitive gyros to measure it, because it's only 15 degrees per hour. So if you're talking about fairly high stability gyros, it's no problem. We can measure the earth rate. If we're talking about the low-grade sensors, they may have a drift of 100 degrees per hour, and you cannot really measure the earth rate with this type of gyros. So we need to find an alternative approach. An alternative approach, the second vector can be a velocity vector. You can assume in the navigation frame you measure it with a GNSS. You have velocity from there. And in the body frame, it can be assumed that your velocity is aligned with the front axis of the vehicle, such as the front axis of the airplane shown here. Another option is to use magnetometers. And I have to say that really the initial alignment doesn't have to be super accurate. You just have to bring the attitude errors into the linear region of the extended common filter, and it can take it from there. So in other words, in the velocity vector example, if it's misaligned a little bit with the frontal axis of the vehicle, it's not really a big issue. You can still use that approach for the initial alignment. So the second question I wanted to cover is the use of motion constraints. How do you actually apply some knowledge of the dynamics of the specific application to improve your dead reckoning performance? And really, we can pretty much use the integration approach, the GNSS Inertial approach, integration approach, and extend it to incorporate the use of motion constraints. In general case, the motion constraint is just a nonlinear function. Again, in the very general case, nonlinear function of position, velocity, attitude, acceleration, and angular rate, and this nonlinear function is 0. So we do the same thing we're doing with the GNSS. We have a minus predicted constraint, and then compare it with the actual quote-unquote measurement, which is 0. Then take the difference, linearize it, and then apply the results for the extended common filter, use it to update inertial error state vector. This is the example here. For automotive application, we can assume that we have a 0 cross-track velocity. So the motion constraint in this case is the velocity vector transformed from a navigation frame into the body frame and then projected onto the y-axis of the body frame. So we have this nonlinear motion constraint, linearize it using the first-order Taylor series expansion, and then use the results for the common filter as a common filter measurement observable, again to estimate drifts in inertial navigation outputs and correct them afterwards. The interesting thing here is that because we need to do the transformation of the velocity from a navigation frame into the body frame, this common filter observable is sensitive to attitude errors, and attitude error becomes observable, which is very helpful, especially for low-grade inertial sensors, because attitude errors, especially heading, is pretty hard to observe in a general case. And this is all what I have for this part of the discussion, and with this I'll give it back to you, Mark.
Great, thanks a lot, Andre. And we're at the first opportunity for our experts to address some of the questions. So the first question I'll actually throw out to Xavier, and that question is, in your opinion, will the upcoming GNSS systems, such as Galileo and BeiDou, obviate the need for the type of integrated systems you're talking about here?
Thanks, Mark. With the additional satellites, it'll make the positioning more available, and you get better urban canyon reception. However, I mean, we're still talking about a system that's 20 kilometers up in the air above you, with quite a weak signal that has to pass through the ionosphere and everything to get down to you. And it's also a system that's widely used, which means people focus on attacking it. So I would suggest that it is very easy to block GNSS, and it is very easy to get denied from GNSS. So I think there will always still be a need for additional systems to complement the GNSS for periods when it's not available.
Great, thanks a lot. The next question I'm going to throw to Andre. Does the reliability of a system, so the ability to detect measurement errors, depend on the type of integration strategy or integration filter that you're using?
It definitely depends on the integration strategy, not so much on the integration filter. So when we're talking about the integration strategy, when you're talking about the loose coupling in an urban canyon kind of situation, you won't be able to have many measurements to really cross-check them against the inertial solution. Versus tight coupling is much more, you have much more room to play there. So the answer is yes. When you're talking about the integration approach, loose versus tight versus deep integration, then the more advanced integration approaches they give you more more options to detect bad measurements. When you're talking about integration filter, to me, when you build in the INS plus something integration filter, whether it's a classical common filter or a particle filter, you still have a prediction and a measurement. And as a result, you can still compare your predicted value versus the measured value and use that to detect bad measurements. So in this case, obviously, the specific numbers will be different. What's your confidence in your reliability check for the common filter versus the particle filter? But conceptually, it shouldn't hurt you to go from one type of filter to the other one in terms of your ability to detect reliably measurement outliers.
Great, thank you very much. The next question, actually there's two questions, I'm going to merge them together and I'm going to throw them to our sponsor, to Jay. These come from Naveen and Noel. How much does the 1750 accelerometer and gyroscope cost? And correspondingly, are there any restrictions or export restrictions, perhaps by ITAR, on the unit? Jay.
Okay, thanks, Mark. So the question is a little bit difficult to answer because it does depend on quantity and things like that. So I'll give a generic answer. We sell the 1750 IMU, which is just the gyros and the accelerometers, as a standalone product, and that is roughly $20,000 in small quantities. Now that number is going to change higher and lower depending on a number of factors. So if you need more precise information, please contact us. In terms of the restrictions, especially ITAR, this product was specifically designed so that there are no ITAR restrictions. It is a COTS or commercial off-the-shelf product, and it is not an ITAR restricted or ITAR controlled item. Mark?
Oh, very good. That's probably very good to know for most of our audience who might be looking to buy one of those. I'll throw the next question out to Xavier. This is a question from Raphael asked directly to you, asking how you can provide 0.05 degree heading accuracy with gyros that have a stability of 0.05 degrees stability itself. He says, with this bistability, you should reach at most 0.2 degrees secant latitude. And I was hoping you could expand a little bit on that.
The way we do that is with the fusion of a lot of sensors and an AI algorithm. And probably I won't answer this question in too much detail because it's expanded upon in my next section.
Okay, fair enough. I will turn the floor back over to Mike for our next poll question. Mike.
Thank you, Mark and Andre and Xavier. I'm going to launch the second poll, so if you'll keep an eye on your screen, it should be up there right now. And again, as you did last time, choose one. And what we want to know is which type of IMU technologies have you had the most experience with? Is it MEMS? Is it RLG? Is it FOG? Is it electromechanical? Are you not sure or none? Go ahead and choose either one. Choose one of 1, 2, 3, 4, or 5. And I'm going to share the results, and they should be up in your screen momentarily. And here they are. Mark?
Yeah, I can't say I'm overly surprised with this. MEMS technology is certainly very hot right now, and people are trying to make the most out of these sensors. And I think as a result, they're going to be quite intrigued to hear what's coming up in the second half of our presentation, where we start to talk about some of the details of how at least this one particular product that's been developed has tried to tackle some of these challenges. So having said that, I'll turn the floor back over to Xavier, who's going to talk a little bit more about the integration of GNSS INS in their specific product. Xavier.
Yep, okay, so in this section I'll detail the implementation into the finished product that is Spatial FOG, shown on the screen. Spatial FOG consists of the KVH 1750 IMU on top here. Our section is the black base here. So that's our gear in there. It's kind of like a sandwich layer that we've put together. So I'll go through briefly how each of the sensors is used in our filter. The accelerometers are used to provide body acceleration, which is double integrated into position, and the primary principle of INS. They are also used for the reference gravity vector and motion analysis, which I'll touch on shortly. The gyroscopes are used to provide angular velocity, which is integrated into angular position to track orientation. They are also used for north-seeking gyrocompassing and again motion analysis. Magnetometers are not used in the traditional sense to provide heading. Instead, they are used to speed up the north-seeking gyrocompass alignment on startup and also to help track gyroscope bias. The barometric pressure is used to stabilize the vertical velocity, which helps to track the gravity vector. When good satellite coverage is available, the GNSS is used to provide position, velocity, and time. When there is poor satellite visibility, the GNSS is used for speed and zero velocity updates using carrier phase deltas from as few as one satellite. For ground vehicles, an odometer can be used for speed updates by measuring the average pulse period and also position delta updates through pulse counts. Other sensors can be used for velocity, speed, or zero velocity updates, orientation or zero rate updates, and position updates. So the filter uses multiple simultaneous correction sources. It tracks the history of correction standard deviation and predicts future correction standard deviation. The reason it does this is because typically the standard deviation that's provided by sensors and systems, it has some degree of error in it. And our filter implementation tries to estimate what that error is to get a better idea of the true error of that source. Attitude corrections based upon the gravity vector can introduce error from linear accelerations. To reduce this, the filter predicts and compensates for linear accelerations. So balancing inertial bias tracking and north seeking is the biggest challenge, and this goes back to Raphael's question before about how you do that, and it is quite tricky. I'll go into it a bit more now. The magnetometers. In this system, we wanted to do away with the tedious manual magnetic calibration that's so often required with systems that have magnetometers. We have implemented a fully automatic magnetic calibration algorithm, which is actually a series of 3 different algorithms that all work together to do the automatic magnetic calibration. And in the filter, as I said, the magnetometers are not actually used for heading, but they're used to speed up the north-seeking initialization. Then during operation, the magnetometers are used primarily for zero yaw rate updates, and this assists in tracking the z-axis gyroscope bias, which is the key to achieving the heading accuracy with these grade of gyroscopes. By using the magnetometers in this way, it makes the system immune to magnetic interference. The GNSS in the system provides position, velocity and time during normal operation. When a fix is not possible, the carrier phase delta is used for the velocity updates, zero velocity and speed update for driving vehicles. It is a tightly coupled architecture, but completely GNSS independent architecture, which means for applications like underwater, the GNSS can be completely removed, and the filter has no tight dependency upon the GNSS. It does have RTK available for applications requiring high accuracy positioning. Also, it features RAME FDE for safe operation. One of the technologies we implemented, which again assists with getting the accuracy, is motion analysis. Now, motion analysis is an artificial intelligence algorithm, analyzes the patterns in inertial data and learns them, and then when it sees the same patterns come back again, it can determine the conditions. A few of the main things it does, one of the big ones is zero velocity updates, which helps to reduce position error growth and also track accelerometer biases. Another one is zero yaw rate updates, and again that assists in maintaining heading accuracy. And for forward driving vehicles such as a car on the ground, it is able to do full speed prediction, which really helps a lot under GNSS outages. So it is kind of like a simulated odometer. One of the core technologies we developed is hot start ability. So it's basically battery backup, a sophisticated battery backup system that it doesn't have a battery that will wear out. It's a new type of battery that won't wear out. And basically, when the system loses power, it retains its previous position, velocity, heading, bias model, and error model. And when the system starts up again, it has that all ready to go, which allows it to start the full navigation filter very quickly. And it starts immediately with heading, it knows its biases, and can track everything very quickly, which really drops down the initialization time. While the power's out, the time's tracked with real-time clock, so you have accurate time immediately on startup. Additionally, the almanac, ephemeris, position, and time are stored, which are then sent to the GNSS receiver to get a hot start on any position fix there. And some of the main advantages of hot start is it allows for high accuracy orientation quickly. It gives you very fast recovery from power outages, and it's ideal for vehicles that don't move when they're powered down. But even vehicles that do move when they're powered down, it can still give assistance through retention of the bias models. So timing and update rate are critical in these systems. A high update rate will reduce your integration error as well as a number of other errors, but it does require a very high level of computing power and careful balancing of resources and a lot of optimization. So to achieve this high update rate, we designed our own safety-oriented real-time operating system, specifically designed for the requirements of inertial navigation and reading in all the sensor data at a very high rate and balancing it all. Direct memory access, or otherwise known as DMA, is the key to balancing resources and achieving accurate timing. And our safety RTOS makes extensive use of DMA, as well as the standard operation of the system. Everything's double buffered DMA, and every DMA channel is filled on the processor. And to be able to run it all, you need a very powerful processor with a floating point unit, and for the nonlinear filtering that we do, you need a lot of RAM. And then in terms of integrating external data, everything comes in with a different delay, and this causes a problem where you can't use old data if the filter's current. So everything has to maintain like a historical buffer, which uses a lot of RAM. And also you have to know this delay. So one of the things our system does is it has a delay estimation algorithm. And so when you first start up, some of these external sensors will take a few seconds to come online while the system is estimating the delay of that sensor. As you run in operation, it will estimate the standard deviation of that sensor as well, as these systems always tend to have some error in their standard deviation. So some of the external navigation aids that are possible with Spatial FOG, local RF positioning systems. These are like ultra-wideband technologies that can be used for indoor navigation, which is very popular at the moment. It can also be used for industrial applications such as like warehouse navigation for industrial robots. Some of the big ones for robotics are rangefinders. So up there on the top right, you've got a scanning laser rangefinder. And this can be used to give you zero velocity updates, speed updates, as well as yaw rate, and as well as like positioning if you start to model things. Another one that is popular, especially in industrial, is RFID position tags. So you might have a ground robot that's driving around on the factory floor, and it's accumulating an error over time from the inertials and its odometer. And eventually it passes over one of these RFID position tags to correct that error. One of the other big ones that's happening at the moment is Wi-Fi, predominantly for indoor navigation, and this is very hot with smartphones at the moment. Vision and stereo vision are other ones that are very interesting. You're able to do zero velocity updates, speed updates, positioning, and also yaw rates. If you are able to have external markers, you can do full orientation from vision. One of the other ones is stereo audio, which can be used for locating. That's mainly useful for position updates and zero velocity updates. And then there's the big one that everyone is working on at the moment, and that's SLAM. That's mapping using any combination of these technologies to map your environment. For example, if you're indoors, map the walls around you, and then once you've been through there, you have the map. You can use that to recognize your position and know exactly where you are, and then that can be used for full position velocity updates. So some of the applications of spatial fog is excellent for navigation through GNSS outages and jamming. It gives you great navigation in tunnels, indoor environments, and around structures obstructing satellite view. It's beneficial for aircraft to maintain navigation through rolls that can cause degraded GNSS visibility. It's a great one for safety-conscious autonomous vehicles. A variant of spatial fog is called sublocus. So both of this is sublocus here on the left and sublocus DVL on the right. Both of these feature the same 1750 IMU integrated. They're specifically designed and optimized for underwater navigation. This one contains a Doppler velocity log, which uses acoustics to bounce off the seafloor or the water layer to determine your velocity. Both of these systems use a high level of motion constraints to allow for superior navigation performance underwater. And that's all from me, Mark. I'll hand that over to you.
Great, thanks a lot, Xavier. Quite a in-depth product you have there. Turn it back over to Andre for the last part of the presentation, where he's going to talk a little bit about beyond GNSS INS integration, which I think is set up very nicely by what we just heard from Xavier. Andre, it's all yours.
Thanks, Mark. So I'm basically going to talk about some aspects of how we extend the system design beyond GNSS inertial integration approach. And specifically, I'm going to cover two aspects: how you can adopt the development results of GNSS inertial integration to include other sensors, and how do we go from a classical extended common filter implementation to include nonlinear estimation techniques, specifically particle filters and marginalized particle filters. So in terms of how do we extend the integration approach to include other sensors, for the generic integration approach, we're still using inertial as a core sensor because it's a self-contained sensor, does not depend on any type of external environments, cannot be jammed or interfered with, and it works in any environment at any time. So other sensors provide reference data when available to reduce drift in inertial navigation outputs. And we still operate within the paradigm of the complementary filter. So we're not trying to estimate the motion states, we're trying to estimate errors, inertial errors in those motion states. As a result, dynamic modeling becomes much more simpler as compared to modeling errors is much more simpler and reliable as compared to modeling motion states themselves. So very similar to the case of the GNSS inertial integration, we have INS-based predicted measurement. We compare it against the actual measurement and check the difference, linearize it, or use nonlinear estimation techniques and use the results, apply the results for estimation of inertial drift terms. So I'd like to use a specific example as a case study to illustrate how we can actually use the development results for the GNSS inertial integration and apply it in a fairly straightforward manner for the integration with other sensors. So Xavier was talking about the using of carrier phase delta changes or temporal phase changes for the integration with the inertial. So what happens when we're using the carrier phase for the integration with the INS, in order to eliminate integer ambiguities, we take difference in carrier phase measurements over time. And that difference, it turns out that it's directly related to delta position or position change between carrier phase updates. So as a result, it can be used fairly efficiently for estimating drift terms of the inertial navigation systems without the requirement of resolving integer ambiguities, which can be extremely challenging, especially in GNSS challenged environments where you have a limited number of satellites and you cannot apply your traditional ambiguity resolution techniques. So the delta phase or temporal change in the carry phase, again, is directly related to the projection of your position change vector onto the line of sight vector between the receiver and the satellite in this case. Also, you have a change in the receiver clock bias, and that's the additional unknown additional state in the Kalman filter. So if you represent this carry phase observable, which is specific to GNSS inertial integration in a generic format, what we have is some projection matrix multiplied by the delta position and some projection matrix D multiplied by the bias state. So this is a fairly generic representation of the carry phase observable for the extended Kalman filter for the case of GNSS inertial integration. So it turns out that we can actually apply this generic representation for integration with other sensors. So the only thing we would have to do when we design the integration filter, we would have to change those projection matrices H and D and pretty much keep our development results the same. So here are a few examples of the sensors that can apply the same generic format that we just talked about when we talked about the carry phase inertial integration. Odometer, you have a position change projected onto the forward axis of the vehicle. A two-dimensional LiDAR, position change projected onto X and Y axis of the body frame. And finally, another example here is a 3D LiDAR where we have a position change projected onto a normal vector of a planar surface that is extracted from a LiDAR image. So for all those three examples, we can pretty much keep all the development results. We don't have to redesign our integration filter from scratch. We can use the results of the GNSS inertial integration and just modify the projection matrices. Obviously, we also have to modify some filter parameters such as measurement noise and process noise, but all the rest of the development you can basically use it for integration with other sensors without really redesigning your whole system. So another topic what I wanted to talk about is the use of nonlinear filtering techniques and extension of the extended Kalman filter to support nonlinear aiding measurements. And this specific topic, it gains more and more interest as we're trying to incorporate some fairly non-traditional source of navigation information to help the inertial navigate better in GNSS challenged or GNSS denied environments. An example is a map matching where you have a hallway layout and you want to restrict your solution within that hallway, or Wi-Fi fingerprinting when you're doing a power match. So for integration with the INS, my favorite thing is the extension that uses a marginalized particle filter. Well, before we start talking about the marginalized particle filter, let me explain in fairly brief and conceptual terms what the particle filter is. So when we have a particle filter, we actually have, it's a Monte Carlo simulation essentially. So you have a multiple realizations of your random process, and then you're trying to select the realization which fits best to your measurements. And the way it's done, you compute the likelihood of each realization based on the measurements and then weight all the realizations. The problem is when you're trying to apply the particle filter to the inertial integration, generally you have quite a bit of states for the inertial, 15 or 18 states. And as a result, if you're using particles to model all those states, it just computationally becomes extremely intensive. So the marginalized particle filter partitions the error states into linear and nonlinear subspaces and uses particles only for those states that actually require nonlinear representation. Generally, it's position states and maybe sometimes attitude states, heading states as well. And then the Monte Carlo particle approximation is only applied to nonlinear subspaces, while the rest of the states are represented by the traditional extended Kalman filter. In this case, essentially what you have, you run a bunch of extended Kalman filters. Each one corresponds to a specific realization of your random process, and then you weight those filters based on nonlinear measurements. So you initialize the system based on some a priori knowledge, for example, derive it from a Gaussian distribution or a priori hallway information, and then propagate it. Once your aiding measurements arrive, you use those aiding measurements to update the weights of your particles. An example here, an integration of low-cost MEMS inertial, vision, partial GPS, and with only 2 visible satellites and a hallway layout. So in this case, initially, the particles are distributed within the hallway, uniformly distributed within that hallway. And then once we get aiding measurements, the solution converges to the true solution fairly quickly. The resulting trajectory stays in the hallway. Obviously, the constraint that we apply here, each particle that crosses through the walls gets 0 weight immediately and is eliminated from the solution. So here's an example of how the example of simulation results of applying the concept of marginalized particle filtering for the integration of inertial with other sensors, and specifically for incorporating the hallway layout information. And the good thing here is that when you designing the marginalized particle filter, the design results for the extended Kalman filter, you can use your extended Kalman filter core from your GNSS inertial or whatever other type of integration you had before without really redesigning and modifying the linear part of the system. You only have to redesign the non-linear part. And with that, I'll give it back to you, Mark.
Great, thanks a lot, Andre. So that concludes the kind of formal presentation part of our webinar this afternoon, well, afternoon for me at least. Before we go on to the next steps in the XE Experts, I'll turn it back over to Mike for our final poll question.
Terrific. Okay. We're going to do poll number 3, and I will be launching that right now. So if you'll take a look at your screen, in this case, select all that apply. And what challenges, if any, have you experienced with IMU technology? Again, select all that apply. Is it 1, performance, accuracy limitations, 2, data communications, 3, size or weight, 4, interface connection issues, or 5, none? And Mark, I'm going to ask you to share your analysis of these.
All right, so it's pretty straightforward response, I think, in this particular case. Certainly the performance and accuracy limitations are something that everyone's striving to try and tackle, and hopefully some of the things that you've heard today will help you address some of the challenges you guys have faced going forward. That said, in addition to the presentation that you've heard today, which will be available online, there is also a bit more information that we have available for you, and that's shown here. So if there's more information about some of the technologies and stuff, you're certainly welcome to visit the KVH website. Or if you have specific questions, you can email Sean McCormack at the address listed there. In addition, on the Inside GNSS website, there's also going to be a PDF of this presentation, as well as a list of resources that have been put together for you to follow up with additional information and maybe fill in a bit more of the details that we couldn't put here in the interest of time. So having said that, we turn now to our second Ask the Expert section. We'll begin by asking a question to Xavier. The question is, do you require a form of context awareness before applying any of your motion constraints? And if so, what type of information might be used to determine that?
Okay, so there's a number of different motion constraints that are applied. A variety of them don't need context awareness, but then there's some that do. And the way we do context awareness is with what we call a vehicle profile, where you select what kind of vehicle it is. So for example, a car, where you know it's going to move either forwards or backwards, with about a maximum of 3 to 5 degrees slip. You can use that to your advantage to take speed updates and estimate your position forwards. In terms of like a human, if you're having an inertial system mounted on a human, you can detect steps using the accelerometers and do stride estimation. So a combination of step detection and stride estimation. That can give you zero velocity updates, and position delta updates. Yeah, there's a number of other motion constraints, but I won't go into further detail.
Great, thanks a lot, Xavier. Next question is to Andre. And this question, Andre, is talking about some of these filters that you've talked about and how people have heard of different types of nonlinear filters, sigma point Kalman filters, spherical, simplex Kalman filters, and all these different things. Can you comment a little bit on the differences between them?
Sure. So basically, you have two approaches for extending the Kalman filter approach. One is to try to incorporate nonlinear terms, use second-order terms such as one-centered Kalman filter, and the other one is it's completely, in a sense, different approach. It's a Monte Carlo type of simulation where this is where you use particle filters. In this case, you're not really approximating anything. You do have some measurement model, obviously, and some dynamic model for the state propagation, but you don't apply any approximation. You just generate a bunch of random processes and really seeing which one fits the best to the measurements that you're getting. So really, two different approaches. One is trying to extend the Kalman filter by using higher order terms, and the other one is trying to use Monte Carlo simulation. Obviously, when you extend in the Kalman filter, you still apply the Gaussian error distribution assumption. With particle filters, you still need to assume something about your measurement error distribution, but it doesn't have to be Gaussian at all. And that's all I have to say for that.
Great. Thanks a lot, Andre. The next question I'm actually going to turn to Jay, our sponsor. The question I think everybody would like to know, asked by Mohammed, is an almost error-free sensor feasible in the near future? Presumably also low cost, I think, would be another extension to that one. Jay.
Oh, it was a great question until you added in the low-cost aspect, Mark. So there are, unfortunately or fortunately, depending on your viewpoint, laws of physics that everyone has to abide by. And until they change those laws, we can get to a very, very accurate, very precise set of sensors. And what I'm talking about are, a combination of fiber optic gyros and accelerometers, and just to throw it in there, GNSS as well. But the question then becomes, it's a balance of a couple of things. It's size, it's cost, and those are the two primary things that you have to take into consideration. At KVH, most of our customers are pushing us to get to a certain performance range, but they have size and weight restrictions as well. And there may be some other things in there that they really want us to achieve. So we're driven by the markets, and of course the markets are controlled by price. So cost is a critical factor. So right now, let's think about the 1750 IMU. The gyros that are within the 1750 IMU are 0.05 degrees per hour of bias stability. A fiber optic gyro accuracy, that's one of the better measures of the accuracy of the gyro, depends on a number of factors. And we could drive that down to near zero, and I believe that's what Muhammad is asking, is something along those lines, a near zero or absolute zero sensor. We could drive it down, but it would drive the cost way up, and it might even drive the size very high as well. Hopefully I've answered the question. Mark?
Great. Thanks a lot, Jay. Didn't mean to put you on the spot there, but I think everyone was wondering. Next question, back to Xavier. Question about whether or not dual antenna GNSS systems are worthwhile, and perhaps some comments as to why you haven't really talked about that too much in your particular application.
So dual antenna GNSS systems are great for providing high accuracy heading when you're both stationary and moving. And we do actually support dual antenna heading with Spatial FOG through using an external GNSS receiver that sends in the corrections to do the moving baseline RTK. However, because of the focus with Spatial FOG has been north-seeking, and the north-seeking works really well, we kind of focused upon the north-seeking. We felt that there's not a great deal of applications where dual antenna GNSS heading is actually necessary. We have some other products that can't do the north-seeking that do use it, but certainly for Spatial FOG, the north-seeking really, it gives you the same sort of heading accuracy.
Very nice. Thank you very much. Andre, just a quick question for you now. Are there any additional challenges associated with integrated GNSS and INS when you have high dynamic applications? For example, if you have put this on a rocket or something along these lines.
Right. Well, I think if your sensors are adequate for your application, then you shouldn't have any additional challenges. What I mean by adequate, your sensors have to be able to measure the dynamic range of your application. Your GPS receiver or GNSS receiver has to track the dynamics with its tracking loops. And inertial, for example, sensors, they have to be able to measure the entire specs of vibrations. If they do that, then there shouldn't be any additional challenges, because in the filter, we model inertial sensor errors, not the dynamics of the application. So again, if your sensors are adequate for the dynamics, then you shouldn't have any problems, any additional challenges.
Very nice. Next question is back to Jay, actually. So Jay, the question is, there's been a lot of talk about the inertial part, but what type or quality of GNSS receiver do you use in your system?
KVH is the inertial quote-unquote expert, if you will, and that's what we do best. We have worked with other GPS receiver manufacturers in the past, and typically it's up to them to provide things like RTK and other attributes of the GNSS system. The integration of the inertial with the GNSS is the key. That's really the if you will, the most difficult part of this this whole sensor fusion solution or approach to the problem. In this case, Advanced Navigation has done its integration and its approach and has come up with what we both believe will be a very precise, low cost, relatively low cost for the accuracy that it does provide, integrated GNSS IMU solution. You know, as far as the 1750 IMU itself, or any IMU that KVH manufactures for that matter, without offending Xavier or Advanced Navigation, it's GNSS agnostic, meaning that it will work with any GNSS or GPS receiver. We don't do that integration per se, but there are several companies, including GPS, GNSS manufacturers, as well as systems integrators that perform that task. So, smart.
Great, thanks, Jay. Xavier, one more question for you. A question about the computational load of the nonlinear filters compared with Kalman filters, and perhaps whether or not that is significant in your particular applications.
Nonlinear filters definitely are significantly more computational resources. I mean, when we first started with our filter, it actually couldn't run in real time in MATLAB, and then on a full desktop PC, and then we had to try and get that onto an embedded system, and we thought it was just going to be impossible. However, you really can like push the envelope with optimization, and it's just optimize, and it is possible to bring the computational load down to something that is like reasonable and feasible.
Great. Thanks a lot, Xavier. In the interest of time, I'll just ask one more question here. A very forward-looking one came in from Glenn, so I'll actually put this out to the entire panel, and perhaps I'll get you, Andre, to address it first. And that is, what types of non-positioning sensors, in addition to the ones that have been mentioned, seem the most promising for integrating with GNSS INS systems going forward?
To me, I think video cameras is obviously one of the sensors that is gaining a lot of interest right now. And any type of maps, magnetic maps or Wi-Fi, or if you have hallway layouts, that's a very beneficial type of information as well. Specifically, when you're talking about really low-cost MEMS sensors, this is really application independent, sensors. If you are talking about more application dependent, such as automotive, for example, then odometer is a very, very valuable sensor. Very simple, but can be used very efficiently to improve your dead reckoning performance. So back to you, Mark.
Great. Xavier, anything to add to that?
Yeah, so probably our main focus at the moment is the human senses, which is vision, stereo vision, and also acoustics. So those are areas that we're interested in and focusing on at the moment, as well as like indoor positioning using RF technologies.
Very good. And Jay, anything to add from the inertial side?
No, Mark, not really. I mean, I think Xavier and Andre have answered it adequately. Thank you. Back to you.
Very good. So with that said, I'd like to actually thank everyone, all of our panelists, Andre, Xavier, and Jay, for your time and your information. I think it was very valuable, and hopefully the audience has taken a lot from that. And Jay, I'll turn it back over to you for some closing remarks from you as the sponsor.
Okay, thanks, Mark. Thank you very much, everybody, for participating, especially everyone who registered and listened today and hung in there. It's a long time. It's a tough part of the day to listen to a webinar. We really appreciate your attending. We trust that the information that was presented was interesting and prove of value to you. If there's anything that you didn't ask today, just contact us directly, www.kvh.com, and you can find me. You can find Sean McCormick as well. And send us an email, and we'll get right back to you. So at this point, I think I'm going to turn it back to Mike Agron to conclude today's webinar. Mike?
Thank you so much, Jay, and Mark, and Andre, and Xavier. Excellent presentations. And folks, we're about that time, and we want to thank you again, as everybody has. We really appreciate your interest and attention to be part of these. Just a reminder, you're going to all be receiving a short survey as soon as you log off the webinar. We'd really love to have you weigh in and let us know how we did today. We value your feedback, and it helps make us better for the next one. I also want to thank our logistics producer, Patty Van Hooser, for all of her behind-the-scene collaboration and working with our speakers. We know they have a day job, and yet you'd never know that this wasn't the most important thing for them to do today. So thank you, Patty, for that. And you will all be receiving next week an email with a link to today's webinar. You'll have an on-demand recording that you can watch 24/7, and that's something that you should see in your inbox next week. Most importantly, thanks again for joining us. Have a great rest of the week. And as your host, Mike Agron, thank you. Talk to you soon. Bye for now.